So we're about there, folks. Hey, it's official. Welcome back, everyone. I don't have a great deal of announcements, but I think we'll talk a good amount of this to start off. Aside from that, we're just about ready to finish off section 5.3. And 5.4 is a pretty short section. We'll probably have that one finished off when we come back on Thursday's next class. But definitely the bigger thing we should talk about is the upcoming exam. This class is interesting for a number of reasons. One of the reasons is there's two sections here, but there's really in spirit three different sections in this one class. There are people who come in physically to the classroom, people here with me today. There's people over Zoom, and some of them might be on a Pocatello campus. And this is also a fully online section right here, which means some people might not even be in state. There's a few people in the classroom who are out of state currently. So doing exams is a little bit tricky, but we'll definitely make it work. Let's go down here for our upcoming exam. I'm just about completed writing our first exam, and what I'll be doing on Wednesday, just tomorrow, is I'll be sending out exams to testing centers. With some people, I have specific arrangements on a specific testing center. There'll be a lot of people who are taking the test on the Pocatello campus, and I just learned the process. What I do is I send the exam to the Pocatello testing center, then I send them a roster, and then I'll contact you to phone in with them to schedule the exam. So that's how that process is going to work. And I'm going to begin it starting on tomorrow morning. So when we come back on Thursday, you'll already have the email from me saying, contact the testing center with this number to schedule your exam. For folks who are very remote, I'll be doing the exam proctoring myself over Zoom on a different day. So we'll be having the exam here physically, and I'll proctor the exam on a different day for the far remote students. So that's our arrangement so far. And if you're not sure where you're taking your exam, don't hesitate to ask anytime, either over email, over class, or over Zoom, and so on. Still a lot more I want to talk about exam one, but I think saying where we are taking the exam one is the most important thing. Jamie asks, is there going to be any kind of review? We don't have a formal review for our exam, but when we come back on our Thursday of this class, I will take any questions that folks have relative to the exam one. So we don't have a formal review on the schedule, but I'll always start class by taking questions. Other questions or comments so far? Okay, aside from that, on this week, our exam one will be held on Tuesday, and that's all we're doing Tuesday. So there won't be a class. The exam is only going to go up to section 5.4. And again, this is a pretty short section. We should be on target for finishing this on Thursday for sure. And if you have lots of questions about the upcoming exam on Thursday, we will address those. So it can turn into an impromptu review depending on student questions. Also, I want to make a note of 5.4 is special. It's kind of like the odd one out. It's the last one. I'm not changing the due date. I still want a 1-week turnaround on this section, but the due dates are more for pacing than anything else. If you're completing your work by the due date, you are considered on track for the class. You're completely caught up. So this being really close to the exam one means the 5.4 question is really going to be one question. It'll be the more basic question from this set right here. I'm not going to go for anything kind of out of order or wild because I understand that we're just seeing it and doing the homework with it. You might not have gotten your feedback on that homework. Well, any questions so far, folks? Okay, so that's the exam content. Other things you should know about the exam one is exam one and exam two are closed calculator and closed notes. But for all exams, I'm going to be including in a formula sheet. This sheet will change depending on the exam. I did make one change. I had a change of heart on what I was going to include there. So let's highlight this. Anything that's not on the sheet would be considered material you have to memorize for the exam. But this is the stuff that, well, you should still try to memorize it, but it's okay if you are a little bit foggy. So these are the things that you'll see as the real last page of your upcoming exam one. You can tear off this sheet and use the back of it for scratch paper, solve your exam side by side. This is quadrant one of the unit circle, all the reference angles. So I felt like this is the one I wasn't too sure if I want to include or not. I feel like this one is a good one to include on an exam. I'm going to include the Pythagorean identities mainly because I had some feedback on last class. We went through them pretty fast, so I think it makes sense to put them here to make them available. This is just in case it comes up, but I don't know if I'm going to ask too many questions directly from there. Aside from that, it could still be useful, so this will be that page in notes. Then anything not on this page is considered material we should have memorized for the upcoming exam. Any questions about that so far, folks? Okay, so this will be provided as your last page. And that means there's certain problems that or certain concepts we do have to memorize. I try to give hints here and there, and this is one of the bigger hints. Expect this question to be a real question on upcoming exam one. It's so important that I think it's good to even indicate it's there so that we're ready for it and we're really trying to memorize these things. It's very important to know what tangent is, cotangent, secant, and cosecant are in terms of sines and cosines, because that's another one of those concepts that kind of is a make or break kind of concept. Being foggy on what these equal exactly makes everything you do in trigonometry a little bit extra harder. Other things we can talk about on exam one, usually we have a lot of things to talk about, is the sample problems. This is a set of problems where if you can solve these cold without looking at any notes or anything at all, you're probably going to get a really great grade on the exam. If you open them up, they might look kind of familiar because these are the lecture notes. All I've done is I've taken out all the definitions, all the terminology, all the theorems, that kind of stuff. Now it's just the problems. If you can still solve these cold without any assists, then you're on great track. These are the kinds of questions that make real good exam questions. And that's how I try to write out the lecture notes. I wouldn't bother you with a question that is not useful for an exam, so all of these are considered great questions. And by the way, because section 5.4 is the last one out, again, expect a nice question. That one's kind of hard, and the last two aren't too bad. The last two make pretty good exam questions. So that's one set of notes for studying. Jamie asked, how many questions are going to be on the exam? You know, that is a really good question, Jamie. I don't have a specific set of number of questions because sometimes I can write a question that includes multiple parts. For an example, one question could be something like this with maybe 4 or possibly 6 parts. That could be one question. And if I did that, we're looking at maybe a 4-question exam since that's a significant amount of time just right there. So I try to keep the questions pretty tame for this class. I'd say for a set of expectations, expect about 5 to 9 questions on a typical exam. On this exam, probably more around 5 or 6 questions altogether. But more important than the number of questions is the actual length of the exam. This is a 2-credit class, which means we meet for only 50 minutes. So I'm constrained with a 50-minute exam. That means I'm probably going to try to write an exam that's truly 40 minutes in length, with the extra 10 minutes baked in for double checking your work, making sure everything is just the way you want it. Does that make sense so far with that question, Jamie? Awesome. So this set of documents is, this set of problems is really pretty long, but I can't ask everything. Kind of my objective when I go to write an exam is I'm trying to look for a representative sample of questions. I'm not going for the questions that would get bogged down in, like with a homework, lots of steps or things like that. It's more faster type concept questions that we're going for on a real exam. So this is a pretty nice document. I'm making this my premier document for the review questions because, again, those are the more important problems for the course. If you want additional questions to practice, I would say go over your assignments again. Those same questions are just as good as the other ones, but those are still old problems. If you like, you can go way down to here, the sample final exam problems. If you open up this document, I have on a section by section basis. Oh, and I do have a correction I have to make on here. Like Hayes pointed out, we had an old edition. So that page number is wrong. The problem numbers are right. You would just go to the end of section 5.2. But I'm going to update this document and the page number so it's a little bit more clear. So if you want even more problems, these come directly out of the book on a section by section basis. And you could solve these fresher problems for additional practice. Well, that's just about everything I want to get out so far. Any other additional questions about our upcoming exam? Okay, well, let's jump back into section 5.3. We have one exact problem to leave off on that one, and then the due date for 5.3 will be a week away from today. Then we'll move into section 5.4, right triangle trigonometry. So at the moment, we're not quite here, but this is just a reminder I had to turn to. This will be an official exam question. Only part A, though, not part B. I'm trying not to ask derivations on a real exam. A derivation would be a homework problem at best. Here's our Pythagorean identities. And next, we went down to here, and we started simplifying trigonometric expressions. This is a interesting skill set on its own. It carries over from all your algebra you've done previously. But once we simplify these things, the new skill is we have to see the actual algebraic properties we're using and cut through all the noise, which is the function notation you're looking at there. Simplifying these algebraic expressions is you just train your eyes to see sine theta as one algebraic object. And here's the strategy. I think we briefly talked about this strategy last class, but we did it extra fast, so let's slow down a little bit on it. If you want to solve this algebraically, but it just looks too busy, looks too crazy, take this whole thing and convert it to something else. For sine theta, let's say that's s as a variable, and for cosine theta, let's call that c as a variable. You can then rewrite this whole entire expression by saying it's s times c plus c divided by s plus s squared. Now, we definitely want to know how to simplify this. That's the major objective. But sometimes practicing over here is not a bad idea. So for the moment, let's practice this. Any volunteers for a suggestion of how you would simplify this thing? Good call. And usually factoring should be one of our first thoughts if we're solving equations, adding fractions, simplifying expressions. Factoring is everywhere in all those kinds of ideas. So good call on this one. The numerator has a greatest common factor of c. We can just factor it out. And that leaves behind s plus 1. Because c can distribute back into the group, giving us s times c plus c right here. Now over here, let's take that same step. Observe that cosine theta appears in both terms. The second term, it's the whole thing. And it's a factor on the first term. That means we can factor out a cosine theta. But factoring is a form of division. If you factor out cosine theta, it divides away on this first term, leaving just sine theta. It factors out here. It's really being divided out. This turns into a plus 1. Let me fix whatever happened right there. And this is what it would look like. Cosine has been factored out of this expression. We should pause right here. Does that make sense to folks getting to that step based off what we did here by analogy? Okay, so pretty much that's all we're really doing on that numerator. Factor out the common factor, and same thing with the denominator. That also has a common factor of s. So we're resolving the denominator here. And if you see what the step is, I'd say just take it right here on the notes. This is what we're really going for, and this is just the practice. Well, over here, observe s appears on both terms. That means you can factor it out. Here it is. You have to divide it here now. It's s divided by s, so a 1. Here would be s squared divided by s, so just s. And here's how it would all settle. This is the analogy, and over here, we're factoring out sine theta and getting the same kind of result down below. So let's take that step. Sine theta appeared here, so let's factor it. It cancels off the first term, leaving a 1. There's a plus in the middle. Next, we divide sine into this sine squared because we factored it out. And that leaves just sine theta here. So that's the factoring in the denominator. And over here on the right, this s times 1 plus s is just the analogy of how we got to here. That look all right to folks so far? Okay, well, we factored, we haven't completely simplified, but on the right-hand side, you're basically there. The purpose of factoring is to try to eliminate the common factors, simplifying your expression. So there they are, completely gone. And over here, sine theta plus 1 is the same as 1 plus sine theta. So these cancel out in the same way. This just leaves us cosine theta divided by sine theta. Let me try to get these equalities in a better spot. Cosine theta divided by sine theta. And cosine divided by sine turns into a cotangent. I'm observing a weird coincidence. I didn't think these problems lined up in that weird way, but here we are. This turns into cotangent theta altogether. So this problem we simplified purely by just taking things like cosecant, writing it in terms of sine. That's 1 over sine cubed. Secant is 1 over cosine. But for these kinds of problems, it was more about factoring than anything else. Any questions at all, folks, on getting through that one? Okay, so that's our last bit of the notes for section 5.3. Congratulations, we have finally completed that section. Let's let that save up. That means our official due date is, let's see, we need to change that. It'll be a week away from today, so February 6th looks about right. The last two questions we were just working on were 70 and 71. And so I just wanted to throw out a comment we made before one more time. If you're getting a little bit foggy on solving your 70 or 71, you're really doing stuff like this. What you're always welcome to do is just grab your cell phone, take a picture of the scratch you're working on, and tell me anything about the problem, like, hey, Mike, I'm not sure what the next step, or is this factoring step correct? Any kind of comment that's the heart of your question, provide it. When you email that to me, I'll take a look at your work. I'll mark it up to help you out with the digital pen. And you're always welcome to send questions like that. Even if you have a lot of questions, don't hold back. It is my job to help out. But let's save this. And now we're next in section 5.4, right triangle trigonometry. For a lot of people, if you studied trigonometry in high school, this might have been your starting point. And there's a reason why we didn't start here in our section. It's still valuable concepts, particularly if we're working in some kind of application. The moment you open those notes, it tells us the reason we didn't start there. Right triangle trigonometry is trigonometry exclusively about acute angles, which are angles that measure between 0 and pi over 2, or 0 and 90 degrees in radian measure, or in degree measure. So that's our restriction. In unicircle trigonometry, theta could be any angle, positive or negative and otherwise, but this is kind of a restrictive setting to define functions, and that's why we shunned it in this course. So here's how it goes. We're going to let theta be an acute angle placed in a right triangle. Let's unpack that part of the definition. If we have a right triangle, all we're assisting is that there is one 90-degree measurement somewhere, and it would be the only 90-degree measurement. So you might draw something about like this. So that angle right here is what makes it a right triangle. We're assuming that there's a 90-degree measurement there. So if you're working cabinetry, decks, building, and stuff like that, we're working with a square right there for 90 degrees. Theta is the acute angle, but there's really two acute angles now at this point. They're going to be here and here. You can place your theta wherever you would like. For the illustration, we could put it, say, here. This little angle symbol is not required, but theta you could put right here to indicate it. And now this is where it gets a little bit more interesting. The moment you placed theta, you can place adjacent theta. Adjacent means the line that theta is touching. I never liked that word because there's two lines. There's this one and this one that you might consider adjacent. Yet this one's special. Anyone know what that line segment there would be referred to as? Exactly. That one's our hypotenuse. And so we're not referring to that side as the adjacent. The hypotenuse is always opposite of this 90 degrees. So you'd go here, opposite that way for the hypotenuse. Let's call this HYP for shorthand. So our hypotenuse goes there. And notice in all of our definitions, hypotenuse goes into two spots. So there's our hypotenuse so far. Next, let's go back to ADJ. That's meant to be the side adjacent to theta. And so that means it's this one. ADJ for adjacent theta. When we say adjacent theta, we mean the length from here all the way to here. And when we put hypotenuse, we're meaning the length from here all the way to here. Likewise for the last one, when we say OPP theta, we're really saying the side opposite to the angle theta. You can visualize it this way. Over here is opposite, so OPP to theta. Once we have this diagram, this defines the trigonometric functions, but there is a better way to kind of think about this, a better mnemonic, really. Anyone recall the mnemonic for right triangle trigonometry? Good call. In every class I've ever taught in trigonometry, everyone's known SOHCAHTOA, so that's wonderful. The education system in Idaho is still doing okay, I guess. So let's call this, probably a little bit too aggressive. Let's bump that down. So is referring to sine is opposite divide by hypotenuse. There it is, opposite divide by hypotenuse. Next part of the mnemonic is CAH, C-A-H, and it reads out as cosine is the adjacent side, divide by the hypotenuse. Let's check it out. Cosine is adjacent, divide by hypotenuse. And last is TOA, T-O-A. So there it is, SOHCAHTOA. And this is saying tangent is the opposite, divide by the adjacent. Let's take a look. Tangent is opposite, divide by adjacent. That's our mnemonic. The other part of this, well, if they are the reciprocal functions. So if you've got this down pat through SOHCAHTOA, just flip them and you've got the definition for cosecant, secant, and cotangent. Let's actually maybe do a little bit more color coding to tie this together. Sine is opposite divide by hypotenuse, so that's the O and H in SOHCAHTOA. Cosine is adjacent divide by hypotenuse, so that's the A and H, and the CAH part SOHCAHTOA. And finally, tangent is opposite divide by adjacent. And finally, reciprocal functions on the right-hand side. So that's what right triangle trigonometry looks like. And it's kind of nice. It's more visual in a certain sense. It's easier to draw a right triangle than a perfect circle, but it's also useful in a lot of applications. We'll be doing more of this stuff on the last part of the course, along with law of sines, law of cosines, and such in applications. And that's where we're going to start use calculators to approximate things a little bit more. But for the moment, we're just practicing right triangle trigonometry really briefly. And my first question, I feel like, is really pretty confusing. I would not ask this one on exam 1. It would become maybe more of a fair question if we had, say, more space between section 5.4 and exam 1, but we're just absorbing this information still. So think of this one as homework not on exams, not on exam 1. It says, find the lengths of the missing sides if side lowercase a is opposite of the angle uppercase A, B is opposite of the angle uppercase B, side C is the hypotenuse, and tangent A is 5/12, B is 6. That almost feels crushing when you read all that information, right? It seems just confusing the way they laid it out, but here's a way to think about this. Whenever you see information given this way, there's already a big assumption about how things should look in your triangle. Let's put out a right triangle real quick to illustrate this. I can get that to line up nicer. Let's just imagine it's 90 degrees there. And they're talking about an angle A, let's put it here. The moment you place the angle A in this location, the work is automatically going to assume, or the notation is automatically going to assume, side A goes right there, opposite of A. Next, we would place an angle B here. So that would be a side B, opposite to the angle uppercase B. And this is always going to denote the hypotenuse, side length C. So this kind of information always relates in this way to that sort of diagram. Does that make sense to folks on that diagram there? Okay, now let's relate it to this example. From that information, I would probably just draw a generic right triangle. There it is, we've got a right triangle. Now the length going here to here and the vertical length going here to here, they might be completely wrong in the problem, but the purpose of the triangle is just to organize the information. If it's out of scale, that's okay, it's not as problematic. Let's now pull in the information. The lengths of the missing, find the lengths of the missing sides. If side A is opposite of angle A, let's plug angle A here, and side A here. Side B is opposite of angle B, so we'll place an angle B here, and a side B here. They tell us tangent A is 5/12. That doesn't give us anything to plug into the diagram, unfortunately. But they did tell us B is 6, so we can plug that in. And put C here. So that's how this kind of question would start. Now that we have the diagram, the only additional thing that we haven't used is that. We know that tangent of A is 5/12. So let's just put that on there. Tangent A is 5/12. Let's also throw down a SOHCAHTOA just so it's available in case we need it. Sorry, say again. Exactly, yeah. Yeah, absolutely. That's the trick to get through this one. So this information doesn't tell us the actual size of the triangle, right? But we can still use SOHCAHTOA. This is the next step I would take to connect the thought that Michael was mentioning. If you use the TOA and SOHCAHTOA, you would also say that tangent of A is going to be opposite of the angle A to start. That's this one. That doesn't help us a lot, but let's write it in. Then it's divided by A, the adjacent of the angle. That would be this one, so we're dividing by 6. And so let's take a look. We have A 6, 5/12. Well, they're both tangent A, and that means tangent A, we could take the A over 6 and set it equal to 5/12. Since the equality here is really powerful, it's a transitive property. Tangent A is 5/12 and tangent A is A over 6. Well, those two things are now forced to be equal to each other through tangent A. So here's what we've done. We just pulled in the information, but then we calculate tangent A based on the diagram we actually have and equated those two values. Does that make sense, folks, to that stage? Now, next thing we could do then is we're getting on to that step that you indicated earlier. We're solving for angle A because we need to know the length of all sides. So we're about to find that. Sorry, I said that wrong. We're solving for the side length A here, not an angle A, a side length. There it is, just multiply both sides by 6 and you get A equals 5/12 times 6. When you simplify, you get 5/2 on this thing for A. So it looks like A on this one is 5/2. I'll box this answer right here, because sometimes for these kind of problems, the algebra goes into all sorts of different spots. Any questions at all, folks, on that first step? Or that first side length, rather? Okay, we wanted to find the length of the missing sides, and so there's still one more left to go. We have to find the side length C. That's not so bad because now we can just use an ordinary Pythagorean's theorem. Much like the Pythagorean identity, it's all the same kind of thing. The Pythagorean theorem goes like this. Pythagoreans, sorry, I have to send that one out to each other every time. Pythagorean's theorem says c squared is a squared plus b squared. And now we have both values of a and b. We can solve for the hypotenuse c through that equation there. So that's our next step on this process. So let's write this out. C squared equals, it'll be a squared, so 5/2 squared. Might as well just highlight that whole thing. Plus b squared, not as bad, that'd just be 6 squared. And now we have an equation from which we'll be able to solve for side length c in pretty short order. So let's work this through. First, we'd want to square that whole fraction. So we've got c squared equals 25 fourths altogether. And this is the stage of the problem where if I was proofreading this as an exam question, I would change the numbers because this turns into 36. And I wouldn't give you this kind of problem on a closed calculator exam. It just becomes too irritating at this point. But for a homework question, it definitely would work out just fine. Next thing you would do is put this over 1 because we need the least common denominator. We can find it by multiplying by 4/4. So now we have 25 fourths plus, let's see, 36/4. 6/4 is 24. Carry the 2. We get 144 fourths. That's exciting. Add 25 fourths to that, and we get 169 fourths. So finally, c squared is that when it's all said and done. We can take c equals positive or negative square root 169 fourths. What I've done is square root the far left side and the far right side as well, pulling down to that equation. The plus and minus is kind of silly, I have to admit, but it's more of a good practice. Anytime you square root c squared on one side and something on the other side, it implies two values. But in this diagram, c is clearly positive, so it wasn't as important of a concept. More of a reminder that can come back to get us. Well, let's take the square root. 169 turns out to be 13 squared, so it's just 13 square rooted, and the square root of 4 is 2. So there's our last part of the answer. A side length of 13/2 goes right here. We did, folks. This one is, again, to me, kind of challenging because knowing what value tangent takes does not give you the values on the triangle necessarily. So that's what this was all about. We had to use actual SOHCAHTOA for our triangle to find out what tangent A equals, and then equate this output with this output. And like Michael was mentioning, really, it's only off by a factor of 2 to make it all come out just right. This is the algebra that shows how that all happens. Well, other questions, folks, on this one? Okay, for this problem, think of it as, well, working on building this triangle from this kind of information is a skill unto itself. And then working with SOHCAHTOA at the same time was the bigger takeaways. However, I'd say example 2, example 3, these are more routine kind of exam questions. This is something I might actually ask on an exam. This one's a longer question, so if I asked you this,
you wrote like b is equal to 5/2. It should have been a is equal to 5/2.
Sorry, say again. A is,
Yeah, there, like you wrote b is equal to 5/2. In the box.
oh, right here, 5/2.
Yep.
And let's see, you were saying this should be B, not A?
No, that should be a, but you wrote like b b is equal to 5/2.
Oh, B is 5/2. You were meaning where on the diagram did we write B as 5/2? Sorry, Hayes, I think I'm just a little off on where that question is. A equals 5/2. The 6 looks like a B. Oh, so this right here was just weird looking. So yeah, that should have been, this right here should have been the 6 that came from over here, being multiplied to the right-hand side, and then simplifying to 5/2. Gotcha. Yeah, I wrote that boxed out that A equals 5/2 here, but you could also say it this way. Once I get an actual pen tool, you could have written out as A equals 5/2 would have been just fine as well. I boxed it out this to also show the algebra at the same time, but if you wrote it out this way, that'd have been fine. Same on this one, I wrote an intermediate step and then it equaled 13/2. You were fine to just write C equals 13/2 like that if you like. I also pulled them up into the diagram just to complete it as well. But other questions so far? Okay. Well, again, this one's kind of a tricky one, but it's a good one to get fluent with, be ready to go with. Not for the purposes of exam one. This is a good one for the homework to help us out. Then this one is a pretty good one for exam one. This could be a real exam one question. I would have to make the other questions a little bit shorter because it's slightly longer than normal. It says compute 6 trigonometric functions of the angle A, only the angle A, given these two pieces of information. Lowercase a is 2, lowercase b is 5. There's really two skills here. The very first thing you must do to get through this problem is write out a diagram. So here's my diagram. It might not be to the correct scale, but we're not too worried about that. This is just to organize. So here's the right triangle. They're talking about an angle A. You could place that anywhere. You could place it here or here, completely up to you. Me personally, I like to put it in this location, but that's just a stylistic choice. The moment it's set there, you do have lowercase a in this location, and you would have lowercase b here, lowercase c for the hypotenuse on that longer strip. The only thing that's required is if you put a there, opposite must be lowercase a. That helps us out because we know lowercase a is 2, so we can plug it in. We have that lowercase b is 5, so that plugs in right here. So really the only thing we don't know about this diagram is the value of c. We might as well complete it and calculate it right there. First, any questions, folks, with setting up the diagram? Okay, if you're okay with going from information like this down to that kind of diagram, then that's the first concept. You're in great shape to start the problem. And you know, the next thing I'd probably do is, even before finding C, I'd probably just start organizing. It wants all 6 functions, so let's start writing it out. Sine A, cosine A, tangent A. So that's the ordinary functions. On the right column is the reciprocals. Sine is conflated with cosecant of A. Cosine goes to secant A. And tangent goes to cotangent A. Okay, so that's our objective. Complete all those outputs for the angles. Next thing you might do is think in terms of let's get that in right. There we go, TOA. And you'll observe, we can actually do the last rows. We can calculate tangent pretty much immediately on this. Any volunteers to show what tangent would equal on this problem?
Two over five.
Good call, folks, in class and in Zoom. I think that was a tie this time. It'd be exactly 2/5. And let's show it this way. Tangent is going to be opposite, and when we say opposite of A, we're referring to this one, so 2. Next, tangent also has the adjacent side, and by adjacent, we mean the 5 there. So we automatically get 2/5. That means you can go to cotangent and simplify this or evaluate this one immediately. It's the reciprocal of 2/5, so it turns into 5/2. So we're already a third of the way done. That's kind of fast, just knowing that information. But for all the other four trigonometric functions, they involve c. So we have to calculate that at some point. Let's do it right now, say over here. It begins with Pythagorean's theorem, c squared is a squared plus b squared. Then we just start dropping in that information for b and a right here. So we've got c squared equals, throw it a 2 here and square it, then add, in place of b squared, grab the 5 here from the diagram and square it as well. Now this is turning kind of nice. This is 4 plus 5 squared for 25. Gives us a prime number of 29. Kind of inconvenient in a certain sense, but that's okay. You square root both sides and you'll get c. This time let's just go and write in the positive because we're anticipating it. Positive root of 29. That doesn't simplify because 29 is prime, and we can throw it up here now. Root 29. So there's really a few squills being asked in this kind of question. We needed to know how to create the diagram, so that will be an exam question potentially. We also need to know Pythagorean's theorem to get this length, root 29. And the last bit is SOHCAHTOA and the reciprocal functions. At this stage, we can just go right down the line. Any volunteers to do the sine A to start us out?
It's 2 over square root of 29.
Yep, exactly. So we'll take opposite of A, that's the 2 you found, and then root 29 for the hypotenuse. I mentioned before, there's not too much value of actually rationalizing at this stage when you're outputting 6 different functions all at once. If I was taking an exam, I would take 2 divided by root 29. It's perfectly fine the way it is. Come over here and just take its reciprocal, root 29 over 2. No reason to fuss too much about this. Even though the number looked a little bit awkward, this is still a really good exam problem. There's no need to do any kind of simplification. You don't have to approximate this. We have the dead-on exact answers. All that's left is a cosine. Any other volunteers for the cosine value? Exactly. So awesome. Thanks, Hayes. So in class and in Zoom, I think another tie. It's 5 over root 29. That means the moment you found this, you've also found secant. It doesn't matter if this is right triangle trigonometry or unit circle trigonometry. A value here implies a value here. So we've completed this chart by putting root 29 over 5. And hey, we did it, folks. That's a bona fide potential exam question. Any questions or comments at all getting through this one? Okay, there is a lot to absorb, but the mnemonic criteria is a pretty powerful one. We need to be familiar with Pythagorean's theorem, but maybe the bigger takeaway is we need to know how to get through this diagram, this information to produce the diagram. If that ever gets a little bit foggy when you're doing the homework problems, go to this part in the notes. This is pretty much what your diagram looks like always, and you just fill in the information. Well, let's take a look at the last problem for the notes today. This one could also be a pretty good exam problem, but I have to admit, this one makes me incredibly uncomfortable. Every time I write down a right triangle, I don't know why, but for some reason or another, I usually go like this and put a right triangle there. If you are like me and you draw your right triangles the same way every time, that can come back to haunt you because there is no requirement that the 90-degree angle has to be here. It could be out here just to see what we'll do with that information. So watch out for those kinds of things. I don't think I try to go for trick questions, but this one could be an unintentionally tricky question just based off this diagram. Sorry, say again? Oh yeah, absolutely. One important fact about these kinds of triangles is the sum of the interior angles of the triangle must be 180 degrees. That's 90 degrees here, and these two form the remaining 90 degrees of the problem. So we need two things. We need to know the hypotenuse length, And we need to know the length of A. Well, it's a right triangle, so because we're absorbing this information, no judgment if you put down SOHCAHTOA on your exam. In fact, it's encouraged. It's a pretty decent mnemonic. Of which one? Yes, absolutely. So you can work with angle A, the 30 degrees, or you could work with the 60 degrees. Either one is just going to be fine. If I was working with 60 degrees, let me tell you the angle I would pick. Well, we want to solve for A, and A is an adjacent side. That means I would probably use cosine right here. That would potentially help us out. But then I would have to divide by the hypotenuse. You know, I missed that we don't actually have that. But we might be all right. We might be able to solve for the hypotenuse going that route. We decide to use the angle of 30 degrees and focus here. Now the angle A is opposite to those 30 degrees. What function deals with opposites? That'd be the sine function. So you'd probably want to use the sine function in dealing with this one. But then the more you look at this, you might decide maybe we don't want to use either because we're going to be dealing with the hypotenuse either way. There's a lot of ways to solve this one. We just have to pick a direction. So let's say we do use that 30 degrees. We do use the sine function. We would say, on one hand, sine 30 degrees is going to do this. It's going to take the opposite side, A, divide by the hypotenuse, C. This would make us uncomfortable, I'd say, because now that's one equation, two unknowns, both A and C. That's not something we can work well with. So we might not want to use sine nor cosine on this one. Looks like tangent is probably the better one, because if you're dealing with tangent, here's the good news. With a tangent function, you would take the opposite. Let's say we're working off those 30 degrees. Opposite would be A. That's an unknown. But then you would also divide by the adjacent. That's a known, and that tells us you probably want to use a tangent or a cotangent on this problem. Let's give tangent a try and just see what happens. So let's do tangent at 30 degrees. On one hand, tangent at 30 degrees is going to be opposite side A, divide by, coming back over here, the adjacent side, which is 10 right here, a length of 10. Let me see if I can fix my color coding a little bit better. So that's tangent of 30 degrees. And that's one equation with one unknown. We can solve this. Except, well, there's another thing you could do. What is tangent 30 degrees? I probably would give you radian measurement on this kind of problem just to help out, but for dealing with degrees, it's good to know what this is really. 30 degrees is pi over 6. So we're dealing with a tangent of pi over 6. What's tangent? It's sine over cosine. So now you have sine pi over 6. Divide by cosine pi over 6. We know how to evaluate those. Sine at pi over 6 is 1/2. Cosine at pi over 6 is √3. Divide by 2. That simplifies to 1 over √3 when you cancel the divisions by 2 here and here. They would just cancel off completely. So this is one approach. Tangent 30 degrees evaluates to 1/3. But on the same token, tangent of 30 degrees is A divided by 10. We can take both the pieces here and here and now equate them to each other. Any questions so far to that stage? So we've got A tenths is now equal to 1 over √3. Let me put the yellow highlighting just to show where those came from. This 30 degrees has less meaning, so we can take that off. Now, when we solve this equation, just multiply both sides by 10. Let's do it, say, right here to visualize it. The left-hand side is just a, and the right-hand side is 10 over root 3. That's one of our answers already. So let me box out this one just to show it ended up here. And here it is, 10 over root 3. So we've got this side now. Now we need the side length C to finish off the problem. Any questions, however, to that stage? Oh dear, I wasn't looking at the clock. Looks like we ran over time as well. We still want to solve for the side length C on this one, so maybe this will be a question we do come back to, just to finish off 5.4 before we get to the next section. But any questions or comments so far, folks, to that stage? Okay, sorry for running out of time on this one. Usually I try to look at the clock a little bit better. I think this was just a fun problem. If you're still working on this and you want to finish it off, what you have to do is solve C squared equals A squared plus B squared. But I'll leave the notes at this stage and we'll come back to finalize it. Well, thanks, folks. Thanks, Kiana. If you have any other questions, don't hesitate to stick around. Otherwise, have a great evening, folks, and I'll see you all in Thursday's class. And just a reminder again on Thursday, if you do have questions related to exam review type questions, don't hesitate to ask them in class. I'd be very happy to help out, even if we spend a lot of time doing them. We'll see you all on Thursday then.
Thank you.
Thank you.
Have a good one.